Hey everybody, welcome back to chemistry, and we're continuing on through chapter 8. And so now what I want to talk about is how there really is a duality with light, and that in some experiments light can be thought of as a wave, as we sort of talked about previously, but in other experiments light can be best described as a particle. So up to about the year 1899, all the data that we had about light could be best explained by the idea that light was a wave. Also, when we looked at this data, we did not have to at any point assume that light was behaving like a particle. Any kind of a data we got could be explained easily assuming light is a wave. So this was sort of an idea that was part of classical mechanics at the time. What we also saw at the time is that if you really wanted to understand what the wavelength of a light wave was and what its frequency was, you could just plug it into that formula there, that C is equal to a wavelength times frequency. However, by the time 1900 rolled around, there was new data that was coming out from studying atoms and molecules. And this was data that sort of described how atoms and molecules either absorb or release energy. And what this new data did suggest is that you could not explain this data using the assumption that light was a wave. Instead, you had to maybe change the rules a little bit to explain how this data was. And so I want to go over this data. And so one of the pieces of data that could not be explained assuming that light was a wave was something called blackbody radiation. What blackbody radiation is if you take some kind of material object, it could be like a chunk of iron or a chunk of steel or a chunk of coal or something like that, and you heat it up until it is so hot that it glows, then it is said to be emitting blackbody radiation. So let me just kind of give you sort of an example of that. So let's say that you are in your kitchen and you're looking at your stove and you're looking at the burner of the stove. And the burner, to start with, is at room temperature. There are going to be steel molecules in that burner, and they're going to be vibrating back and forth at room temperature. As it turns out that any kind of atoms or molecules that are vibrating back and forth in place, because there are charges associated with these molecules in the forms of negative charges and electrons and positive charges and protons, because these atoms or molecules are vibrating back and forth, it is a rule of classical mechanics that suggests that these molecules will release energy and it'll be radiation. Now the thing is, if you're at room temperature, the wavelengths of this radiation that is released is going to be in the microwave range or the infrared range, and so you won't be able to see it. Now, let's pretend that you turn on the heat to your burner, and so what happens is electricity is going into the burner, and so the electricity causes the burner molecules to vibrate faster, and so they're vibrating faster than the molecules have a higher temperature. And so if the burner gets hot enough, you get those molecules vibrating fast enough, you will start to see it glow a color, and that color is going to be a very dark red color. Now, how hot does the burner need to be for you to start seeing it glow as a dark red color? It has to be at about 525 degrees Celsius, which is almost 1,000 degrees Fahrenheit. If you were to continue to heat up that burner, what would happen is you will observe that as it's getting hotter and hotter, then it goes from, say, a deep red color to sort of a normal red color, and then it starts going into an orange color, and then more of a yellowish color. If it is able to get hot enough, it could get up to a sort of a white hot color. And so this is sort of the idea of blackbody radiation, is that you can heat things so hot that what they're going to be doing is they're going to be releasing a lot of electromagnetic radiation, not so much in any particular wavelength that is released, but it's going to be a spectrum of waves. And so I sort of have this plot of what blackbody radiation looks like for various temperatures of a substance. And so what you can sort of see is if you look at the top curve, that would be a substance heated up to 6,000 degrees Kelvin, which is going to be, I guess, it's going to be 5,700 degrees Celsius. If you heat up a substance that hot, what you're going to see is that substance is so hot, the molecules are vibrating very fast, and they're releasing all kinds of wavelengths of light. And so what you can see is sort of on the right side of that graph, they're releasing very long wavelengths of light that you can't see, so they're releasing microwaves and infrared waves, but the curve goes up, and you can see that most of the waves that are being released are in the visible region. And also what you can see is that you don't have any particular color that's released. You're seeing all kinds of colors released. And so blackbody radiation, again, releases a spectrum of colors. Now, at cooler temperatures, you still have a spectrum of radiation that is released, but you can see the curves are more shifted to the right. So at cooler temperatures, say the lowest curve, which is at 3,000 degrees Kelvin, you can see that most of the radiation released you're not going to see. It's because it's going to be in the microwave and the infrared, and only a small portion is going to be in the visible spectrum in the red. Okay, so one of the things that the scientists of the time kind of saw was that you could not use the laws of classical mechanics to predict the curves of the spectrum when you have black body radiation for a particular temperature. So to give you an example of this, let's say you have some kind of object, and let's say you heat it up to 5,000 degrees Kelvin, and so it will start glowing at that temperature, and the reason is because the molecules are vibrating really fast and releasing all kinds of wavelengths of energy, a full spectrum of energy. Now, if you look at that graph on the left there, you see that green curve on the right of the graph. That is the prediction of the intensities of the particular wavelengths that you should get if black body radiation followed the rules of classical mechanics. Now, that is the green curve. That is what is expected. But the actual data you get from an object that is at 5,000 degrees Kelvin is with that red curve there. And what you can see is that the red curve is different than the green curve. The green curve, the curve predicted from classical mechanics, does not fit the data of black body radiation well at all. And so the main assumption for the green curve that was made is that the radiation that is produced from that substance, the black body radiation, that electromagnetic radiation, that spectrum of light produced, is going to be in the form of a wave. However, if you change that assumption that this radiation is not in the form of a wave, but instead the radiation is released as particles, if you change that assumption to a particle assumption, then the actual data actually fits what you would expect predicted if you assume that the electromagnetic radiation is released as a particle. And so at this point, this was sort of the first data that suggestion that not all experiments can you assume that electromagnetic radiation can be described as a wave. Black body electromagnetic radiation can only be well explained assuming that light is not a wave, but it actually behaves like a particle. So the person who sort of first figured this out was a guy named Max Planck. He did this in about 1900 in Germany, and he was, again, able to explain the data from black body radiation, assuming that light acted like a particle. For example, if you see a spotlight, and you're in the spotlight and you're being exposed to light, he basically said that that light that's coming toward you is not waves, but trillions and trillions and trillions and trillions of individual little particles. Each of these particles, he said, had no mass. These particles of light that are hitting you are called photons. Now, another thing he's saying is that these particles of electromagnetic radiation are coming from the vibrating molecules, and that when they're vibrating back and forth, they are producing these particular particles. Now, another thing that was kind of important he was saying is that when they're vibrating back and forth, it's not so much that you can get a continuous range of energy that can be released from these vibrating molecules. Instead, you get discrete numbers of particles. These particles that are released from the vibrating molecules, and there'll be numbers like 1 or 2 or 3 or a zillion particles, he calls these particles quanta. And so if you have one quantum of an energy particle, it'll have a specific amount of energy that will depend on the frequency of the light that is being emitted from the molecule. And so you can actually use an equation to understand exactly how much energy was in this particle, this photon of light that's being released when it has a particular frequency. And that formula there is written there as E of the photon is equal to a constant h, which is called Planck's constant, times the frequency of the photon. We're going to have to probably solve some problems using this equation. What you're going to have to probably figure out is, given that you know the frequency of light, can you figure out what the energy of a photon of that particular frequency has? So the formula there, as I just kind of mentioned, is that the energy found in that particular photon is going to be equal to Planck's constant, which I'll give it to you in a minute, times the frequency of the photon in hertz. This will give you the value of energy found in a single photon. Now, what you might have to do is you might be a problem where you have to find the energy found in a lot of photons. And so there you just sort of modify the equation slightly. If you can find the energy for a single photon, you just take that amount and multiply by the number of photons you have, and that will give you the total energy of the photons. So let's go ahead and try this practice problem that we have here. It says a photon has a wavelength of 624 nanometers. Calculate the energy of this photon in joules. What is the energy of a mole of photons of this wavelength? Okay, so let's go ahead and see if we can solve this problem. Okay, so we have a photon that has a particular wavelength. It's at 624 nanometers. And what we're trying to find is the total amount of energy that that one photon has. So there is an equation that we can use, and so that is the energy of the photon is equal to that constant, Planck's constant, which will be given to you on the test, times the frequency that that photon has. Okay, so what you can see in this particular problem is that we're not given a frequency per se, we're given a wavelength. And so what we're going to have to do is maybe modify this equation so that we can throw in wavelength into it and get the energy of the photon. So that's not so difficult to do. So you might also remember previously that when you're dealing with electromagnetic radiation, the speed of light is equal to the wavelength of the radiation times the frequency of the radiation. Now this also applies to photons as well. So if you have the speed of a photon, which is the speed of light, this is given to you, it's 3.0 times 10 to the 8 meters per second, which is the speed of light, is equal to the wavelength of the photon times the frequency of the photon. So what we can do is, we have in this problem, we have wavelengths. And so let's go ahead and solve this equation for wavelengths. And so I'll just leave out photons just to make things a little bit clearer. And so wavelength is, or excuse me, let me try that again. What we're going to do is we want to here solve for frequency. So frequency is equal to the speed of light divided by the wavelength. Now what I can do is I can substitute c divided by wavelength into frequency here, into this equation. So the energy of the photon is equal to, give you a better equal sign there, okay, is equal to Planck's constant h, and then we're going to substitute into frequency here the speed of the photon divided by the wavelength of the photon. So it's going to be times c divided by wavelength of the photon. And so at this point, I think we can just sort of plug in numbers and get the answer. So you will be given h, and so it'll be 6.626 times 10 to the negative 34 joules per second. C you'll be also given, which is 3.00 times 10 to the 8 meters per second. And then wavelength in this problem is given to you, which is 624 nanometers. And so one of the things you might imagine is that you're probably going to have to convert the nanometers wavelength into meters. And so let me go ahead and do that now. So it's going to be times 1 times 10 to the negative 9 meters over 1 nanometer. So nanometers cancels. And so the number I get by multiplying these together and again, I'm not going to really use good scientific notation here, but it's correct, is 624 times 1, which is 624, times 10 to the negative 9 meters. Okay, and so we can go ahead and at this point plug it into this equation and find the energy of this photon. So the energy of the photon is going to be equal to, and it looks like I'm going to need a little bit more room, is going to be equal to h times c over lambda. So what's going to be equal to is 6.626 times 10 to the negative 34 joules per second, multiplied by c, which is 3.00 times 10 to the 8 meters per second, divided by wavelength, which is 624 times 10 to the negative 9 meters. Okay, so let's just see if units cancel the way we kind of hope. We're trying to find the energy of a photon. So what we're kind of hoping is that the units cancel out, so we're left with an answer in joules. So it looks like meters in the numerator here cancels out with meters in the denominator here. Let's see, meters per second. Oh, I should have said here with Planck's constant is joules times second. That is correct. So the seconds here in the denominator cancels out with the seconds here in the numerator. And so it looks like we're going to be left with an answer in joules. And so if you work out the math, it's going to be 3.19 times 10 to the negative 19 joules is the energy found in one photon. So if that's the case, you can imagine what the energy would be found in 2 photons. It would be twice this energy, right? If you had 3 photons, you multiply this by 3, and that will give you the total energy of 3 photons. Now then the question we want to address in this problem is, okay, how much total energy would there be in a mole of photons? So how would you figure out that? Well, that's not so bad. So one thing you might remember is that 1 mole of anything is equal to 6.022 times 10 to the 23 of that anything. So usually it's applied to, say, atoms or molecules, right? So if you have 1 mole of atoms, that is going to be 6.022 times 10 to the 23 atoms. Well, you can also apply it to photons, in that if you have 1 mole of photons, it's going to be equal to 6.022 times 10 to the 23 photons. So we can use that relationship and the energy found in 1 photon to figure out the total energy in 1 mole of photons. And so it would be just this. It would be 3.19 times 10 to the negative 19 joules is found in 1 photon. And we're going to multiply this by a fraction such that we can get the number of photons to cancel to get an answer in a mole of photons. And so what I would write here would be times 6.022 times 10 to the 23 photons over 1 mole of photons. Okay, and so what you can see is photons cancel out, and so we're left with an answer in moles of photons. And so if you multiply 3.19 times 10 to the negative 19 times 6.022 times 10 to the 23, you should get that number there, which is 1.92 times 10 to the 5 joules. And so this is the energy found in 1 mole of photons. Okay, so let's move on to a new problem. Okay, so we have this problem here. It says a laser emits light, has a frequency of 4.60 times 10 to the 14 hertz. The first part of the question is, what is the energy of 1 photon of this laser? Okay, so this is not so difficult to solve, and so we recall that the energy of a photon is equal to Planck's constant times the frequency of the photon. Okay, and so what we can do is maybe hopefully just plug in numbers. It looks like we can do that. So Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. And then we're going to multiply by the frequency of of the light, which is composed of these photons, and the frequency is 4.60 times 10 to the 14 hertz. But when you see hertz, that's like saying per second, or having second in the denominator. So it's going to be 4.60 times 10 to the 14, and I'm not going to write hertz, I'm just going to write per second like this. And so what you can see is that the seconds will cancel out, and so we should be leaving with an answer in joules. And so if you take 6.626 times 10 to the negative 34 and multiply it by 4.60 times 10 to the 14, you should get the energy of the photon. So I'll write energy of the photon for one photon is going to be 3.05 times 10 to the negative 19 joules. Okay, the next question is, if a laser emits a pulse of energy containing 5.00 times 10 to the 17 photons of this radiation, what is the total energy of the pulse? Okay, so that's not so bad. What we now know is that at this particular frequency of light, which was 4.60 times 10 to the 14 hertz, a single photon will have this amount of energy, which is 3.05 times 10 to the negative 19 joules. And so now what we're wondering is, if we have 5.00 times 10 to the 17 photons, how many total joules are there in that number of photons? And so that's not so bad, right? So we have 3.05 times 10 to the negative 19 joules. And again, this is the energy in one photon. And now what we're trying to do is figure out the energy in that large number of photons. And so all we do is we multiply this by 5.00 times 10 to the 17 photons. And you can see the photons cancels out. And then you can multiply these two numbers together, 3.05 times 10 to the negative 19 joules times 5.000 times 10 to the 17. And so the answer that you should get is 0.153 joules. So that will be the energy in this very large number of photons, 5.00 times 10 to the 17. Okay, and so the last question is, if the laser emits that amount of energy in that problem there, which is 1.3 times 10 to the negative 2 joules of energy in the pulse, how many photons are emitted in that particular pulse? So here we have 1.3 times 10 to the negative 2 joules in a particular pulse. And what we're trying to do is figure out, okay, if one photon of this particular frequency, if one photon has this amount of energy, which is 3.05 times 10 to the negative 19 joules, how many photons would be required to give us this energy in the pulse, which is 1.3 times 10 to the negative 2 joules? And so that isn't so bad. So we know that one photon here is equal to 3.05 times 10 to the negative 19 joules. And so you can set up two fractions. You have to pick one. And so the one I'm going to pick is going to be times one photon over 3.05 times 10 to the negative 19 joules. And so what you can see is that joules cancels out, and you should get an answer in photons. And so if you take 1.3 times 10 to the negative 2 and divide it by 3.05 times 10 to the negative 19, that should give you the number of photons. And so the number you should get is 4.26 times 10 to the 16 photons. Should be the answer. Okay, so let's move on. Let's just kind of try to sort of summarize a little bit about what we've been thinking about in terms of now light not so much coming to us as waves, but as coming to us as particles, as photons. So imagine that you have two spotlights here, and so you have a blue spotlight and a red spotlight. And let's say that these two spotlights, the blue and the red, although they're different colors and therefore they have different wavelengths, they have the same intensity. What does that say about the number of photons that are coming at you from each of these spotlights? Well, if you have a relatively dim light, that means there are not so many photons that are striking the receptors in your eye. But if you have a more intense light, then you have a lot more photons that are striking the receptors in your eye. So if we have here an example of these two different colored spotlights with exactly the same intensity, these beams of light in both spotlights should have exactly the same number of photons. Now, there are going to be trillions and trillions and trillions of the photons in each of the beams, but again, if the spotlights have the same intensity, the same brightness, then they should have the same number of photons. Now, within, say, the red beam of the spotlight, do the trillions of photons that are there have exactly the same wavelength, frequency, and energy? Yes. Assuming that all those photons in that red beam all are monochromatic, meaning they're exactly the same frequency, then all those photons will have exactly whatever frequency it is. They'll be the same number, and they'll have exactly the same wavelength associated with them. Now, keep in mind that the energy of a photon is equal to Planck's constant h times its frequency. And so you can imagine that of all those trillions and trillions and trillions of photons there in that red beam, because they all have the same frequency, each of those trillions and trillions of photons will have exactly that same amount of energy between them, that quantum of energy that is found in the photon. Final question is, let's compare the red beam photons to the blue beam. Do the ones in the blue beam have a different wavelength, frequency, and energy? And the answer is yes. So you're looking at the blue beam now and comparing it to the red beam. And so even though these beams have exactly the same intensity, and so they have the same number of photons, the blue beam photons are different, that they're going to have a much shorter wavelength. In other words, the crests in these waves, which are photons now, are being closer together, and they'll have a much higher frequency. And so in the blue beam, since these photons, all of them have a very high frequency, what you might expect is that they're going to have high energy. Each of the photons in the blue beam will have more energy than the individual photons in the red beam. And so I just kind of mentioned that